might be interconnecting leads of the resistors or whatever components. So you have a component, if this is a resistor, there might be an error in the connection in the leads of it. What else? There might be a system disturbance. Some disturbance due to measurement. What that means is basically you might, for example, if you want to measure the current, you have to, if this is a voltage source and you want to measure the current, what you do is you add a meter that measures the current going through. So you have to cut the circuit and measure the current. So cutting the circuit might actually lead to a system disturbance. What else? Also inherent or internal supply, which is power source, or meter resistance. So there might be internal resistance in the supply. Also component tolerance, which we discussed in the question 1. Tolerance. So resistance does not necessarily have the same nominal value. So R plus or minus percentage error. What else? There might be also environmental effects. Such as temperature, humidity, and whatnot. Which in that case temperature affects resistance. Now for part B, choose a sensor that measures temperature. So we have 3 sensors that measure temperature that we have studied. The first one is basically the IR barometer. There is also thermocouple or thermistor. Actually there are 2. So let's take the pyrometer as an example. So let's see, how do we draw it? So basically pyrometer is a non-contact sensor, meaning that you don't have to put it on the object or like have it be in contact with the object, touches the object that you wanna measure the temperature of. So the way it works is basically it depends on a property of the body. It's called black body radiation, which says that any object above with a temperature above 0 Kelvin basically it emits electromagnetic radiation. This radiation, there is a relation between temperature and and wave length. So temperature and wavelength. Temperature and wavelength. So they are related. So this is how the sensor looks like. There is basically a detector and an optic. So a lens and a detector, optic and detector, and supposedly the radiation will coming from the object will be directed towards the detector through this. This is emitted radiation coming from basically an object, a hot object. What our resistor does, the IR parameter, is that it detects the wavelength and relates it to the temperature of the object. So it's an efficient sensor when it comes to applications like in ear. If you wanna measure the temperature inside the or if you wanna in the manufacturing of the semiconductor, you need to measure the temperature. So semiconductors are really tiny, so you cannot build a sensor that measures it that is that tiny, so that it measures the temperature. So it's easier to use the IR parameter. Okay, so what are the key aspects again? It's non-contact. Its range is basically from 100 to 3600, and the accuracy of it is basically up to half degrees. However, you still need to know the specific details about the object you would like to measure the temperature of. Basically, which is in that case namely emissivity, which is a constant. Emissivity comes from emission. And finally, it's passive. So now part C. A fire will connect to 1 kilo ohm assuming first of all, you know, it's first step. Simple as this. Resistor, then the ammeter has to be in series with the resistor to measure the current. So resistance, this is 5 volts, resistance is 1 kilo ohm. So ideally, I should be V over R, which is 5 over 5k, 5 over 1k, which is 5 milli. amperes. Now, this K is times 10 to the power 3. Okay, now, so this is I ideal. Now, given that this has an internal resistance, so the new circuit will look like this. This is 10 ohm. And this is 1 kilo. So apparently the current that will appear on the reading of the ampere will be I reading will be 5 over 1,000, just 1k, plus 10, making current 4.95 ampere, milliamps. Therefore, the error is 4.95 minus 5 over 5. Actual value minus ideal over ideal. It's minus 0.99%. That's it. Now for part D, it asks us to describe the term common mode rejection. So basically, common mode rejection is simply a measure of, this is like an op-amp operation amplifier ability to reduce the unwanted signal. So say for example that this is an op-amp. Yeah. Supposedly, if we don't have any signal from positive or negative terminals, we only have a common one. So assume that this is the noise. So the output should be the difference between this and this. In that case, if this is 5 volts, this would be split into half. So we split between both of them. So this will be 5 volts and this is 5 volts as well. But this is in the negative terminal, so it's going to be minus 5 volts. Therefore, V out should be, or 5 volts, but then V out should be the difference between both of them multiplied by a factor. But the difference between both of them should be 0. 5 minus 5 is 0. But usually in non-ideal, so ideally, V out should be 0. But in reality, V out, which is in that case V out common is equal to a small difference, so 0.00 something, for example. So there is a small gain, which shouldn't be there. So this question is asking about this. So again, a measurement of the ability of an op-amp to reduce the unwanted signals. So basically the formula is as follows: the gain due to the difference between both of them plus the gain of the common mode. So this, ideally, the CMMR or the common mode rejection ratio should be equal to infinity, close to infinity. In that case, if we calculated it, 400 given over 0.01, 400 over 0.01, which is 40,000. And the common mode rejection is the same thing, but you add 20 log of this ratio, which is